Now in section 2, we talk about periodic mechanical waves in a more quantitative sense. So we want to put some names to the parts of a wave. So let's say I have a wave propagating in the x direction, and it's a transverse wave, so the disturbance is in this transverse y direction. If I take a snapshot of this from the side, what I see is that I have these nice sinusoidal waves propagating to the right. The first thing I want to notice about this thing is that there are these peaks. There's these troughs and then there's these peaks. The distance between two sequential peaks is going to be lambda, and pretend like lambda is going to be the same, pardon me, for every one of these peak to peak distances. That lambda is also the distance between any two troughs, any two bottom points. And what I want to say is that lambda is the wavelength. And I'm using the Greek letter lambda, which hopefully you've seen before. I also notice that when I look at that disturbance that's happening in the y direction, it'll have some maximum value here for each one of these peaks. And that distance from the top of that wave to the middle point, to the 0 point, is a. And notice that for these troughs, they're going to have a displacement of minus a. So a disturbance on that wave will move from a at the maximum to a minus a at the minimum. And so what we say is a is the amplitude of that wave, or the amplitude of that motion. And so we've defined two important quantities or descriptors for a wave. Now in the same way, if I look at a wave, I look at a point in space and I watch waves pass me, I see this disturbance happening from some maximum a to some minimum a, but it's happening at a point in time. So at a point, what I observe is this. Again, disturbances in the y direction. But if I just plot out what's happening as a function of time, I'm going to see if I can draw a better sinusoidal wave than I did last time. I see this nice sine or cosine wave traveling or happening at that point. Notice again, this is going to be the amplitude of the wave. So the disturbances are from a to minus a. This time though, notice from peak to peak, it's happening in time. So that distance between two peaks is going to be measured in seconds in this case. And I'm just going to call that t, which is the period. And it's going to have units of seconds. Now, if I'm at a point, I also might be concerned with the frequency. And the frequency would just be the number of waves that pass that point per unit time. And so I'm going to define frequency. I'm going to use little f to describe it as my symbol. The frequency is going to have units of inverse seconds or hertz. And importantly, I see a relationship between the frequency and the period, which is f is just equal to 1 over t. And if that's true, a little bit of algebra will convince me that the period is just equal to 1 over the frequency. And you'll use each of these when you look at different problems. So notice we have these sinusoidal waves passing a point in space, and they also behave sinusoidally in time. So I have wavelength, frequency, period, and amplitude to describe these waves. Another thing that I'm going to say is that a wavelength lambda passes a point in one period. So when I look from the side too, I can either see that an entire wave will pass a point in a period t, or in a period t, a disturbance in the wave will travel lambda. And so when I'm looking at this wave traveling again in this x direction, and I see this disturbance, it's moving to the right with some velocity v. But because I know that it travels a distance lambda in a unit of time t, I can write that the speed of that wave is equal to lambda times f, or lambda times the frequency. I just put the frequency in because I had 1 over t times lambda. And I have this expression, which is an important one, in which it's going to describe the speed of propagation of mechanical waves, like sound or vibrations in a surface. And it's also going to describe the speed of sound as a function of, lambda and f for electromagnetic radiation as well. Now, having said that, I can look at a specific case, and we can look at one nice simple example of sound waves propagating in a tube. Now, sound waves consist of these little regions of dense air, and they're equally spaced, and they're moving, in this case, in this tube, to the right with some speed v. Now, the distance between these dense regions, that is one wavelength, lambda. So let's say we've taken a tone, middle C from a piano. Well, this note is characterized by having a frequency of, let me look this up, 262 hertz. And I also know that the speed of propagation of sound in air, or the speed of sound, is going to be, in this example, 344 meters per second. So I can ask the question, what is the wavelength for middle C? And I'm just going to use that simple relationship I know, which is V equals lambda times F. Well, I've been given V, I've been given F, so I know that lambda equals that speed divided by that frequency, which is going to be 344 meters per second. And then the frequency was 262 hertz, which really I can express as, just 1 over a second. So that 1 over a second in the numerator, 1 over the second in the denominator, they're going to cancel each other out. And I end up with an answer just in terms of meters. And I get 1.31 meters for the wavelength of middle C. The other simple thing that we might do is to use that speed of sound. When we see something happen, light travels so fast compared to the speed of sound that it's basically instantaneous. So there's an example here that you're an infantryman and you see the flash of a gun firing, and 20 seconds later, you hear it. And you've probably seen things like this before. You've seen somebody strike something with a hammer at a distance and you saw it happen before you heard it. Well, we can use our knowledge of this speed of sound to find the distance to the sound source. So there's going to be some observer here, and then there's going to be, I don't know if I can draw a gun, but there's some person who's got, pretend that I have drawn like an actual gun and it fires. And what happens is, see the gun fire, and excuse my grammar, but hear the report 20 seconds later. And you know that there's some capital D, some distance between these two people. We're going to ask, what is D? Like I said, when you see it, we're just going to assume that you're saying it right when it happens and you're hearing the sound after it's traveled that full distance D. So remember here that you had the velocity is going to be equal to some distance divided by some time period. And I'm going to assume too, my assumption here is going to be that the speed of sound is again 344 meters per second. And so if I want to know what D is, I just multiply each side by t, and I end up with d equals v times t. And this should be familiar too from the mechanics portion of this class. So I put 344 meters per second times 20 seconds. And what this tells me is that d is about 6.88 kilometers. I've skipped a little bit of a step in here, but I multiplied 344 times 20, and I get 6,880. And I just did a conversion there to kilometers because it makes more sense. This is going to be about 4.3 miles. So you see, as you know, that sound travels pretty fast. You get that 4.3 miles traveled in just 20 seconds. And that's a couple little examples in applications of this relationship V equals lambda times F.